Okay, in this video I'm going to talk about vectors in the xy plane. So let me start with a definition. A vector is a mathematical quantity that has both magnitude and direction. You'll often see vectors in a field such as physics. Graphically, a vector is often represented as an arrow or a directed line segment. The beginning of that directed line segment is called the tail. So the point that begins the vector is called the tail of the vector. The point at the head, at the tip of the vector is called the head of the vector. Okay, so the magnitude of the vector is just the length of the line segment, and the direction of the vector is often measured counterclockwise from the horizontal. All right, let's see a concrete example. Okay, let's find the magnitude and direction of the vector PQ. So the tail is the point 22, and the head is the point 44. So that's how you read this notation. Vectors are often denoted in books. Actually, sometimes in books it has a boldface, or it has a little arrow above it. The first letter denotes the tail of the vector. The second letter denotes the point who is the head of the vector. Okay, let's start by plotting these 2 points. So here we have our vector drawn in the xy plane. So the magnitude of the vector is really the length of this segment right here. The easiest way to find that is to form a right triangle whose hypotenuse is that. So we see that since the tail of the vector has x-coordinate 2 and the head of the vector has x-coordinate 4, this has length 2. Similarly, the y-coordinate here is 2. The y-coordinate here is 4, so this length is 2. So then we just use the Pythagorean theorem to find the length of that, which is the magnitude of the vector PQ. Okay, so we use these absolute value signs to denote the magnitude of the vector. So the magnitude of this vector PQ is 2 square root of 2. Okay, to find the angle of the vector, what we need is the angle as measured counterclockwise from the horizontal. We notice that we know the length of the side opposite this angle, and we know the length of the side adjacent to this angle. So I'll call the angle theta. And so what we have is that the tangent of theta is equal to the opposite divided by the adjacent, or 1. So then the angle theta we find by looking at the inverse tangent of 1. And we all know that that's equal to pi over 4 radians. Okay, so the magnitude of this vector is 2 root 2, and the angle is pi over 4. Okay, press pause while you work on this example. Okay, so you should have constructed your little right triangle that has a side length here of 2 and a side length here of 3. So then you just use the Pythagorean theorem to find the length of the vector, or the magnitude of the vector, and that is equal to square root of 13. To find the direction of the vector, it's measured counterclockwise from the horizontal. So we're actually looking for this angle right here. First up, we have to find that angle. I'll call that alpha. The side opposite alpha is 3. The side adjacent to alpha is 2. So that means that the tangent of alpha is 3 halves. And then alpha is simply the inverse tangent of 3 halves. So if you plug this into your calculator, you find that alpha is around 56.31 degrees. So again, we're not looking for alpha. We're looking for this angle right here. So all we do is subtract that value from 180, and that's the direction. Okay, so we find that the direction of PQ is about 123.69 degrees, and the magnitude of that vector is the square root of 13. Okay, often we have the need to, when we work with vectors algebraically, we have the need to find what's called the component form of the vector. So the component form of the vector PQ, the notation-wise, the enclosure is just these 2 little triangular braces. And Inside are the two numbers. The first number tells you how far you need to go in the x direction to get from point P to point Q. The second one tells you how far you need to go in the y direction to get from point P to point Q. So let me illustrate this through an example. So here I have the vector PQ that has a tail at -2, 1 and a head at 3, 2. To get the x component of this vector PQ, I have to figure out how much I need to add to -2 to get to 3. So we see that we have 1, 2, 3, 4, 5. So we have to go 5 units in the positive x direction. So the x component of this vector is 5. P has a y-coordinate of 1, Q has a y-coordinate of 2. So we only need to go up 1 unit in the y direction to get from P to Q. So the y component of this vector is just equal to 1. So this vector PQ in component form is written as 5, 1. Okay, why don't you find the component form of this vector PQ? Press pause while you work on it. Okay, so the x-coordinate of P is -1, and the x-coordinate of Q is -3, so we have to go 2 units left to get to P. So that gives us an x-component of -2. And then we have to go, so the y-coordinate of P is 2, the y-coordinate of Q is 5, so then we have to go up 3 units from P to get to Q. So that means that the y component of that vector is 3. Okay, the formula in general for the component form of a vector that starts at P and ends at Q is x2 minus x1. So the x-coordinate of Q minus the x-coordinate of P, comma, y2 minus y1. So the y-coordinate of Q minus the y-coordinate of P. We can see that that formula checks out for this example too. So we got the x component of 5. So we have 3 minus a -2. And then the y component of 1, we have 2 minus 1. So among other things, the component form of a vector allows us to tell whether or not two vectors are equivalent. And they are, okay, so they are the same vector if they have the same component form. So we can see here that this vector PQ has an x component of 1 and a y component of 2. So here PQ is the vector 1, 2. Similarly, the vector RS has an x component of 1 and a y component of 2. So RS is also the vector 1, 2. So that means that these two vectors are equivalent vectors.